There are many different types of statistical tests, each designed for different situations, different types of data, or in different types of questions. There are two ways that one can describe and contrast different tests. First, what's the purpose of a particular test? What type of questions is it trying to answer? Second, what are the assumptions or requirements that must be met in order to properly use it? To illustrate this, we'll use what's one of the more basic statistical tests, the one-sample z-test. The purpose of a one-sample z-test is to assess whether the population or subpopulation being sampled has a mean that is different from some specified value. This is typically a value that is believed to be the larger population mean or some value that one expects to see if a treatment effect or a group difference doesn't exist. Now, when we talk about the population or subpopulation being sampled, we're often talking about a real or relatively easy to define group. For example, assume that I know the mean verbal IQ score for all kindergarten students across America is 100 points. Maybe I think the kindergarten students in Colorado have higher verbal IQ scores than the national average. In this case, a one-sample z-test can help me answer that question. I could collect verbal IQ scores on a sample of students from Colorado, and let's say that the average for this sample is 110. While this is higher than the national average, I may have just stumbled upon a few particularly verbal Colorado kids. The one-sample z-test helps me to determine the likelihood that I would have randomly ended up with a sample mean of 110 or more if in fact the population of all kindergarten students in Colorado has a mean equal to the national average of 100. The population may also reflect a more abstract or theoretical case of all people who could receive a new intervention. For example, instead, let's say that I know the mean math SAT score for all the students across America is equal to 500, and I have a math intervention that I want to test. Does it lead to higher scores? A one-sample z-test can help me answer that question. So I go and sample students to take part in my intervention. Note that we can think of them as a sample from a theoretical population of students who could have taken my intervention. After completing the program, these students take the SAT and have a mean score of 530. Now, of course, I could have once again stumbled upon a few very bright students, so a one-sample z-test helps me determine the likelihood that I would have randomly ended up with a group that has a sample mean of 530 if the mean for that theoretical population of students who could have taken the intervention is in fact only equal to 500. In other words, if the intervention doesn't help students, what's the chance that I would have randomly ended up with a group that nevertheless obtained a mean of 530? Notice I'm not asking whether my sample has a mean higher than 500. We already know it does. It's 530. That's not the question. What I'm asking is, what's the likelihood that I would have ended up with a sample who has a mean as extreme or more extreme than 530 if the actual mean for that theoretical population of students who could have taken the intervention is in fact only equal to 500? Moving on, what are the assumptions or requirements needed in order to conduct a one-sample z-test? First, the population needs to be normally distributed. Now, technically, what I mean, no pun intended, is that the population distribution of whatever score we're calculating has to be normally distributed. For a one-sample z-test, we're using the sample means. So, is the population distribution for sample means normally distributed? In other words, if I took an infinite number of samples out of the population and calculated a mean for each of those samples, and then made a plot of those means, would those means follow a normal distribution? If you've watched the video on central limit theorem, you know that if the sample size is larger than, say, 30 or so, the answer is generally yes. The distribution of sample means will get closer and closer to normal, regardless of what the underlying raw data look like. So with large sample sizes, this assumption can be a little relaxed. Now, it does make things easier if the underlying raw individual person data follows the normal curve. In that case, you don't have to worry about what's large enough or how big of an issue is this. Think about it. If the raw scores for individual children follow a normal curve, then of course averages based on any sample size are going to be normally distributed. Even averages for a sample size of 1 will be normally distributed because, well, the individual scores are all normally distributed. A second assumption is that the data reflect a random sample. You can think of this a couple of ways. On one level, the whole point of what we're doing is to generalize back to the population. So a random sample from that population is needed in order for our sample mean to be valid. On a deeper level, some of the statistics and inference involved work because we have a random sample from the population. Third, the data, specifically I mean the outcome variable, needs to be on an interval or ratio scale, meaning that the units for whatever you're measuring are all equally spaced. Finally, a one-sample z-test requires that the population variance, or sigma squared, is known. You're not trying to estimate it. This is usually the deal breaker for a one-sample z-test. Rarely do we actually know the population variance. Well, sometimes we might with population data such as birth certificates or national testing data, but in practice, that's rarely the case. Fortunately, as we'll see in future videos, there are alternatives when you don't know the population variance. So, once you've determined that a one-sample z-test will answer the question that you have, and you know that your data satisfies the key assumptions for a one-sample z-test, you need to formulate your hypotheses. Like many statistical tests, hypotheses in one-sample z-tests can be what is called directional or one-tailed, or they can be what's called non-directional or two-tailed. Let's continue with our math intervention example and first consider a directional or one-tailed hypothesis. Again, for this example, we know the average math SAT score for all students in America is 500. With a directional hypothesis, we might propose that students who receive the new intervention will have a mean SAT score higher than 500. Notice that it's directional because I'm only looking at the score being higher than 500. I'm not even considering whether it's lower than 500. I'll then use a sample of students who receive the intervention to test my hypothesis. Given that, there are a couple of ways that the null and alternative hypotheses can be conceptualized. Mathematically, we can write the alternative hypothesis as mu1 or mu alternative is greater than mu0 or mu0. Remember, in previous videos, we noted that H1 was shorthand for the alternative hypothesis, so that's why we use mu1. It's to indicate that we're talking about the average for the population we're investigating in our alternative hypothesis. Similarly, we use mu0 or mu0 as shorthand for the null hypothesis. So we use mu0 to reflect the overall mean that we're typically comparing our sample to. It reflects the value we expect to see if there's no difference or no effect. Now, what would the null hypothesis be? In this case, it would be mu1 is less than or equal to mu0. Notice that between the two, the null and alternative hypotheses are exhaustive. Whatever happens has to fall into one of these two scenarios. Now that said, sometimes you may see someone write the alternative hypothesis stating something like x bar, or the sample mean, is greater than 500. I just don't like that. We know what x bar is, and we know whether it's greater than 500. We're ultimately not interested in x bar or the sample mean. We want to use it to estimate the population average. It's the population average that we ultimately care about. Worse, maybe x bar is only slightly greater than 500. In that case, x bar is greater than 500, but we may still not reject the null hypothesis because we might have seen many samples with a mean slightly greater than 500, even if the null hypothesis were true. Because we know the overall population mean, mu0 or mu0 here, is equal to 500, we can also write the alternative hypothesis as mu1 is greater than 500. And we can write the null hypothesis as mu1 is less than or equal to 500. In English, we could phrase the alternative hypothesis as the average SAT score for students who receive the intervention is greater than 500. While in English, the null hypothesis would be the average SAT score for students who receive the intervention is less than or equal to 500. Notice that with directional hypotheses, if you predict in the wrong direction, you lose. Let's say the average SAT score in our sample was much lower than 500, maybe 400, maybe only 300. It doesn't matter. You would always fail to reject the null hypothesis because it's less than or equal to 500. Our hypothesis is only testing whether the mean for intervention students is greater than 500. We're not even considering whether it's less than 500. Of course, you can have directional hypotheses going the other direction. It may not make sense, but what if we thought that the intervention students might score lower than the national average of 500? Maybe the intervention's a bad intervention. Our alternative hypothesis would now be that mu1 is less than mu0, or mu1 is less than 500, while our null hypothesis would be that mu1 is equal to or greater than mu0, or mu1 is equal to or greater than 500. In English, the alternative hypothesis would be that the average SAT score for students receiving the intervention is less than 500, while the null hypothesis would be that the average SAT score for students who receive the intervention is equal to or greater than 500. Now, there are also non-directional or two-tailed hypotheses. Continuing with our example, we might propose that the mean SAT score for students receiving the intervention is different than 500. Maybe it's higher, maybe it's lower. I'm interested in either possibility. Mathematically, we can write the non-directional alternative hypothesis as mu1 is not equal to mu0. Again, it can be higher, it can be lower. I want to know either way. What would be the null hypothesis? In this case, it would be mu1 is equal to mu0. Notice that the null and alternative hypotheses continue to be exhaustive. Whatever happens has to be covered by either the null or the alternative hypothesis. Now, because we know the overall population mean, mu0, is equal to 500, we can also write the alternative hypothesis as mu1 is not equal to 500, and the null hypothesis as mu1 is equal to 500. In English, we can say the alternative hypothesis is the average SAT score for students who receive the intervention is not equal to 500. While in English, the null hypothesis would be the average SAT score for students who receive the intervention is equal to 500. With non-directional or two-tailed hypotheses, we reject the null hypothesis as long as the difference is sufficiently large in either direction. So you've determined that a one-sample z-test is designed to answer your question, and you know that the data you have satisfies the key assumptions to perform that test. And you now have your hypotheses. How do you go about calculating the test statistic and determine the p-value? We'll cover that in our next video. Bye for now.